Probability based on cards is not hard as long as you know what cards what makes up cards. Number one, no probabilities use the Joker, so we'll get rid of him. And what's left is 4 suits: clubs, hearts, spades, diamonds. And in each suit, as you go along here, there are 13 cards per suit. All right. And then out of the suits, if you look at the cards individually, they always have an ace. And then they have numbers 2 through 10. So you get your 2 through 10. And then you get your jack, your queen, and your king. Now these guys have their own special name because they're staring at you, or at least have faces, and they get called the face cards. And you can do tons and tons of probability based on cards. The more complex ones would be how to play poker and which hand becomes the most populated hand or the powerful hand by being the least probable to happen. So for instance, if we're looking for the probability of selecting a number card, so that would be the 2 through 10, theoretically, the probability of that event of picking a number card would equal, well, how many number cards are there in a deck? Well, if it's 2 through 10, that's 9 numbers, and that's 4 times 9 for all of these cards, so that would be 36. So the number of the events would be 36 out of the total number of all the cards that are possible in the deck. We're only selecting one card here. Shuffle them up and pick off the top card. Well, if there's 13 cards per suit and there's 4 suits, that means there's 52 cards in all, 13 times 4. So the probability of picking just a number card, let's see what goes into both of these numbers. 4. 4 goes into 36 9 times, and 4 goes into 52 13 times. It is 9 out of 13, which is better than half. Decimally, let's see here. 9 divided by 13 is 69.2%. So about 70%, approximately 70%, or 7 out of 10 times, you will get a number card showing up. All right, so let's go back to my website and just be curious about this. We can change this. We can change the game from a coin to a card. And we're only going to draw one card from a stacked deck. We're going to include everything except jokers and whatnot. And where does this button happen? Let's see. Oh, there we go. Draw a card. All right. So we drew a card, and that card happened to be a king. Well, he's not a face card, so that would be, if we did a recording of this, it's number card or not a number card. So I would set up a little table, number, not number. I'm going to do this on paper because it'll be easier for me. All right, so we got a not number that time. Next time we got a number. Next time we got a face card, which is not a number. Got a number. Got a number. Got a number. Excuse me. Got a face card. Got a face card. Wow, that's unusual. Got a face card. Got a face card. This empirical probability is not going to work out very nice. Got a number. Got a number. Got a number. And eventually, with probability, if you do it enough times, you will get what you're looking for. But in this case, I'm not liking. That's definitely not a face or number card. That's a number. That's a number. That's a number. That's a face. Hey, this thing is stacked against us. Don't play blackjack with these cards. That's a number. That's a number. That's a number. You have to do a little bit more of these because there's 52 cards, and the probabilities won't be good if you choose a small sample size. So let's see here. There's 20 number cards so far and 13 not number cards. So let's see what that turns out to be. All right, so with our experiment, empirical, I only did it 33 times. That's not a lot. And we found that the probability of finding a number empirically is 20 times that actually worked out of 33 times that it actually didn't. This is a lot closer to 66% than it is to 70. So let's see here, 20 divided by 33, 60.1, or no, 61% approximately. So it's not hugely off, but it is pretty far off empirically. But again, if we chose this number to be larger, the probability of selecting that number card out of there would be greater. With this video, I wanted to attempt to explain the outcomes, because sometimes if you just knew all of the outcomes, then finding the probability is actually kind of easy. Now, if you're going to flip, and we'll stick with easy examples, one coin, your outcomes would be it's either going to flip on a head or it's going to flip on a tail. And therefore the probability of a head is 1 out of 2, and the probability of a tail is 1 out of 2 total. So the problems come in when we flip more than one coin. So let's start off with flipping 2 coins. And you have to imagine that one of them is going to be blue, just color it blue, and the other one is going to be red. And we're going to record when the blue coin flips on a head or a tail, and we're going to record when the red coin flips on a head or a tail. And when I record it, it'll be like the blue one was a head and the red one was a tail. So the head-tail is totally different than a tail-head, because the blue one is the one determining the first letter, and the red one is determining the second letter. So if I come up with the sample space or the outcomes of flipping 2 coins, it's possible that both coins flip head. It's possible that I have this over here to the left, that the first one was a head, the second was a tail, and vice versa. Blue, red, blue, red. And then the last one is if they flip 2 tails. So if I talk about probability of flipping the double heads with these 2 coins, the number of outcomes, well, it only happens once right here at the top. So that'd be 1. And the number of events is 1. The number of outcomes is all of them, so that would be 4. So if you're flipping 2 coins, you get 2 heads in a row, the probability is 1/4. If I'm looking for the probability of head-tail or tail-head, or an easier way to say that is when the coins are different, then that probability will be the 2 in the middle divided by the 4 total. So this would be 2/4, better known as a half, 50% of the time. So that's the one that becomes like just flipping a regular coin. Alright, if we expand on that, we could have flip 3 coins. And this one gets a little bit harder. And there's a couple different ways of doing this. One is considered a tree diagram. You start off, you flip the coin, and then it only has 2 choices. It lands on a head or it lands on a tail. Now, if the coin landed on a head and you flip the second one, you kind of think of it as 3 separate coins, or this is the red one, then the blue one, then the green one. Or you can flip a coin 3 times in a row and record what happens over the 3 events. So if it flipped a head on the first coin, the second coin has an option of flipping on a head or a tail. If the first coin landed on a tail, then the second one could have landed on a head or a tail. This is what's called independent events. Flipping a coin, the first coin as a tail, has no effect on what the second coin is going to do. Alright, and then again, if the second coin, well, let's put it this way. If the first coin landed on a head and the second coin landed on a head, the third coin could have landed on a head or a tail. So each one of these is going to get an HT branch. These things get quite big if there's more than 3 events. So first off, the nice thing about tree diagrams is it tells you right away how many events are going to be happening. There's 2, 4, 6, 8, so there's going to be 8 events. To figure out specifically what they are, you either go, well, probably the easier way is to go backwards on the branches. So this one would be H, H, H. And then this one would be T, H, H. Oh, but we're going backwards, so I would write it backwards too. It really doesn't matter, but the way I do it is a little different, and it fits this pattern more. The next one is HTH, so you just go down the branches until you get back to the home. So HTH, and then TTH. Wait a minute, was that there? 1, 2, 3. Yeah, TTH. So this would be TTH, and then HHT, HHT, and THT, THT, HTT, HTT, and then all three of them tails. So here's your outcomes, 8 of them. So if I ask you what is the probability of having 2 heads, kind of like up here where it was 1/4, this gets a little bit different. You have to pick the ones that literally have 2 heads in it. So he has 2 heads in it, he has 2 heads, this one does, and none of the rest. So the probability, the events number, is just 3 out of all of them, which we've determined is 8. So the probability of flipping at least 2 heads is 3 out of 8. The probability of at least 2 heads is a little different. Now when you say at least, you're saying it has to be 2 heads or it could be more. So when I say at least 2 heads, we get to include this guy because he's at least 2 heads. He has 1 more, so that makes him 3. So then the events become 4 out of 8, and we're back to that probability of a half, which is kind of cool. Now, coins also represent children if you make the assumption that if you're pregnant, half the time you're going to have a boy and half the time you're going to have a girl. It's not really half to half, but it's close enough that we can treat coins and children exactly the same way. So this would represent your first child, this would represent the second one, and this would represent the third. So then you could have a boy, 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 a boy, boy, girl, and so forth and so on. So coins and kids generally are the same thing, and you would set it up very, very similar.